For lesson 3 of chapter 24, we are still in section 2 of chapter 24. This is sort of day 2 of yesterday's notes. So still working with some similar concepts. So on the first one, this is really more of review than anything else. But it's always good practice. This is a new concept for students in this course. So here we go with this function that we see right here. And for that, we're asked a couple familiar questions that we should know how to do. So this is one in class. I'll be sort of pausing at this point and having students do this as more like a warm-up because this is something they should already know how to do from yesterday's lesson. So if you're watching this for the first time, you might want to pause right here and give that a try before I go forward with it. But here we go. So first thing they're asking us to do is keep in mind that's just asking us to find the derivative. So dy dx is the same thing as saying f prime of x. It's the same thing as them saying in words find the derivative. They might just say in words differentiate. All those mean the same thing. Anyway, finding the derivative using our power rule. 3 times 2, we get 6. Subtract 1 from the exponent. On term 2, we're left with just the negative 6. And so that would be our derivative. So now find the gradient where x equals negative 2. So this is our x coordinate. You can always plug an x coordinate into a derivative in order to find a gradient. So keep in mind one big highlight from yesterday's notes is simply whenever you plug an x coordinate into a derivative, you get a gradient. Whenever you plug an x coordinate into the original function, you get a y coordinate. So we're using the same number for two different purposes. When it goes into the derivative, it gives you a gradient. When it goes into the original function, it gives you a y coordinate. So important to remember. So what is the gradient where x equals negative 2? Well, let's plug that into our derivative. So f prime of negative 2. So replacing our x with negative 2 in the derivative would look like this. And if we do a little cleanup on that, should come out with 18. So remember what we have now at this point is we have an x coordinate of negative 2. We have a gradient of 18. In order to finish this off, we now need the y coordinate in order to finish off what they're asking us to do here. So far we know that we have an x coordinate of negative 2. We know the slope is 18. And one thing we don't know right now is the y coordinate. So they're saying what are the coordinates of the point where the gradient is 18? Like we said, we already know the x coordinate. All we need is the y coordinate. So if we take negative 2, sub it into the original function, that will give us the y coordinate. And so for this one, if we sub negative 2 into the original function, we get negative 4 as a result. One thing to keep in mind is there can be, as we saw in the last lesson, more than one point where the gradient is 18. So this is one point that we know for sure, but there might be another. So I'm going to check and see if I take my derivative and set it equal to 18, since my gradient is 18. Remember, that's like saying the derivative is 18. If I were to solve this for x, so add your 6, divide by 6, square root both sides, well, what are you going to get on that? You're going to get a plus or minus 2. So there is another point. We already know the negative 2 point is this one. So what about the positive 2? So same thing, if I plug in positive 2 into the original function, looks like we're going to get positive 4 as his y coordinate. So there were 2 points, so I had to make sure I found them both. Something to watch out for as you're doing those. Anyway, all that was review. This is also a review question. So if you look at example 2 part A, this is one that you should be able to do from yesterday's notes. In the previous lesson, they didn't say the gradient is 0. They said you had a horizontal tangent line. But for a horizontal line, it would have a gradient of 0. So this is the same question, it's just worded differently. But anyway, if the gradient is 0, that's like saying the derivative is 0. So I'm going to take the derivative of this and set it equal to 0. So if you go through your power rule on this and find the derivative of our function, so f prime of x So using the power rule on that, you're going to get x squared for the first term, 1x squared. You're going to get 1x to the first. For the second term, -6 right here, constant goes away. So that's going to be our derivative function. And in this one it says the gradient is 0, so I'm going to set the derivative equal to 0 and solve for x. If I solve that by factoring, so most people should be able to factor this one at this point. Factors would be x plus 3 and x minus 2, which means the solutions are -3 and +2. So we know those are the x coordinates, and we're going to sub those into the original function as always to get the y coordinates. So if I were to plug -3 into the original function, I'm going to get this as my y coordinate. And if I plug in a 2, I get -10/3 as my y coordinate. So those are the coordinates where the gradient was 0. And again, I showed you graphically in the last lesson how that works. So one thing you do have the option of doing is graphing this function, and if you identify the max or the min values, right, the maxes and the mins are the points where the gradient is 0. And so these are the coordinates that you would find as a max or a min point on this graph. Set of values of x for where the gradient is positive. So one thing I want you to see on this, and of course graphically this is a great thing to do. I'm going to show you two ways of doing this. One is with what we call a sign graph, as in positive signs and negative signs. So you're going to be asked for this on your test. This is sort of an IB thing, so this is why I'm showing it to you, but this is called a sign graph. A sign graph simply does this. We create a little number line like this. On that number line, we're going to throw in the x coordinates where the gradient was 0. So I'm going to throw a -3 onto that. I'm going to throw a +2 onto that. If the gradient was 0 at those points, that must mean that surrounding them in these areas, it's either positive or negative. So we start by just identifying the points where the gradient was 0. And now we're going to test a number in this area, and this area to see what kind of a slope we are getting. Remember, slopes come from derivatives. So if I were to test a number in this area, let's just say -4. If I took -4 and plugged it into my derivative, what kind of a slope do I get? Do I get a positive or a negative? Well, any number that you pick in this area, if you plug it into the derivative for x, you're always going to get a positive result from any number in that area. So that means any gradient in this area of the graph is going to have a positive slope. Well, if I test a number in this area, so any number between -3 and 2, let's pick an easy one like 0. If I plug any number in this area into my derivative, I am always going to get a negative gradient from any number in that area. So this area of the graph is negative slopes. And if I test any number in this area, so any number greater than 2, and I plug that into the derivative, and you can just test one, like pick a number like 3, plug it in for x, you're always going to get a positive result or a positive gradient for any of those numbers. So here's what we just discovered. We just discovered that any value of x that is less than -3 will have a positive slope, and any number that is greater than 2 would also have a positive slope. So those are the areas of the graph that would give you positive gradients. And so that's one great way of figuring out the answer to that question. The other way to do it is by looking at the graph itself. So let me go to the calculator for a minute, and I'm going to graph this function. So give me just a second to do that. So here you go. I graphed the original function right here, and I'm going to go ahead and graph that. Within that graph, looks like I need to go a little higher here, so I'm going to go to my window, and let's increase my y max. Let's make that guy go a little higher, see if we can't get the whole graph on the screen. Almost. All right, I'm going to go a little higher. All right, one more time. So window, let's go up to 20. Maybe 25 just to be safe, so we don't have to do that too many times. We should get the whole graph now. Here we go. All right, so there's our function. Again, one thing I can tell right off the bat is here is an area of the graph where the slopes are positive. Here's the area of the graph where the slopes are negative. Here again, they are positive. Of course, in between positive and negative, you have a 0. So I know this from what we've already done is -3. Right? So that's where x is -3. Then I go from negative to positive. So in between negative and positive must be another 0. And I know again from what we've already done that this is where x is 2. So based on this graph, if I hadn't even done this yet, let's just say I wanted to find out that maximum point right there. So if I go under calc and I choose max, and I know the max is right about there. So as far as a left boundary, I'll go left a couple times and hit enter. For the right boundary, I'm going to go right a couple times and hit enter again. Let me block that glare for you. So there you go on the graph. I can see right there I have an x coordinate at -3. So just based on that knowledge, I can see from the graph that I'm looking at that everything to the left, or everything that is less than -3, has a positive slope. I could do the same process again over here with the minimum feature to identify that this is 2. And then I could say, well, then everything that's greater than 2 has a positive slope. And so that's another thing that we can do. Not to mention, this is a great way, sorry, I'm trying to block that glare. This is also a great way of identifying areas on the graph where the gradient is 0. Right? Anytime you find a max or a min, that's a point where you would have a 0 slope. Because if I draw a horizontal tangent line where x equals -3, right, then I have a 0 slope. Right? So again, I can see the coordinates at this point where I would have a horizontal tangent line or a 0 gradient. So all those are kind of things that we need to know from that. Moving on. Example 3, determine the values for x for which that function will have the same gradient as where g of x has this function right here. So if I look at those two functions, where would they have the same gradient? Well, that's where their derivatives would be equal. So if I take the f prime of x function, I'll do it right here, kind of keep it isolated. Anyway, if I do my power rule on that, the constant goes away, and 3 times -3 is -9 x squared. So there's the derivative for f of x. The derivative for g of x, using our power rule, would be -1 to the second minus 4. Well, where do they have the same gradient? And this one just says x value, so I don't need ordered pairs here. I just need x's. So simply, if they have the same gradient, that means they have the same derivative. So I'm going to set my two derivatives equal to each other and solve that equation for x. So if I add 9x squared to both sides, that would put me at this stage. Add the 4, divide by 8, and you're looking at x squared equals 1/2. And so if I square root that, we can just square root both sides, and we can say plus or minus the square root of 1/2. Now, I know appropriately in the past, you're not supposed to leave a radical on bottom. This is kind of one of those areas where that's accepted. So you'd be okay at this stage to leave it like this, unless the direction specifically said to not leave a radical on bottom. But this is pretty much something that's accepted for this stage of the game. So anyway, let's move on. Example 4. Find the gradient of that function at the points where it crosses the x-axis. So what does that mean? Well, any point on the x-axis would have a y-coordinate of 0. So any point on the x-axis, we know that the y value is going to be 0. So that's basically what they're telling us. One thing we got to do before we can take a derivative here is put that into friendlier terms. So I will do a lot of distribution here in order to reformat so that I can take a derivative. But if I just think about this question logically for a minute, one thing that we can take away from this setup is if I were to set this whole thing equal to 0, like this is suggesting, what would my solutions be, or what would my x's be? Well, he would be 0, he'd be 4, and he'd be -1. So keep that in mind. We are going to use that here in a minute. But before I can work with derivatives and gradients, I would have to go through some distribution on that. So if you FOIL and then distribute the x, here is the new format that we're going to be using. So you're going to have x to the third minus 3x squared minus 4x. So that means the derivative, using the power rule, would be this. So here we go. Now we have all the information we need in order to answer the question. So what is the gradient where it crosses the x-axis? So again, I know this simply tells me which x values I should be subbing in, right? I know on the x-axis the x values are 0, 4, and -1. So that means those are the three numbers that I have to plug into the derivative in order to find the gradient that they are asking for. So if I start plugging in those numbers, then I can get the three gradients that they're referring to. And so like if I were to plug in a 0 for that, so f prime of 0, I'm just going to get -4 as my gradient. So that's one of the gradients they're looking for. If I plug in a 4 into the derivative, then I would get his gradient. And if I plugged in a -1 into the derivative, then I would get his gradient. So if you just start subbing those into the derivative right here, you're going to get the gradients at those points as well. And those are the three gradients that they are looking for this problem. Well, where it cuts the x-axis, what does that mean? The y-axis, anywhere on the y-axis, we know x is 0. So all this is asking me to do is plug in a 0 into the derivative to find the gradient at this location. So we already know that if I plug a 0 into the derivative, I get a gradient of -4. So that one's kind of already done. So that's what they were looking for that one. So a lot of this just has to do with interpreting what this tells you to move forward. Last one, example 5. So this function has a gradient of 2. They give us a point. Find its gradient when x equals 4. So a couple things we got to take away. Obviously, we need to solve for a and b. That's something we got to figure out. So let's start with that. You have two unknowns. So two unknowns means I need two equations, and we have to solve a system of equations. Well, one thing we know is that when I plug in a 1 for x, I get a result of 6. So that's one thing I can do right off the bat. If I plug in a 1 for x, so 1 to the third is 1. 1 times a is a. If I plug in a 1 right here, 1 squared is 1 times b is b. So here's one equation I can get right off the bat by subbing in this for x and y. The second equation is the derivative is 2. So the gradient is 2. That means the derivative is 2. So if I take the derivative of this, just using the power rule, 3 times a. We do this one off to the side here. So I know that 3 times a is 3a. And this becomes x to the second. Right here, I know that 2 times b is 2b. That would become x to the first. Well, looking at that, again, I now know that if I plug in a 1 for x, I get a result of 2. This is a gradient, so that's why I'm working with the derivative function for this part. But anyway, if If I plug in a 1 for x, I know 2 is the result. So if I plugged in a 1 for that x, I'm just left with 3a. And if I plug in a 1 for the other x, right here, I'm left with just this guy right here. So there's my second equation. And now we have our system of equations to solve. So probably want to use like an elimination process or something like that. I would multiply this equation by -3 in order to set up my x's for elimination. You could also multiply this equation by -2 in order to set up your b's for elimination. So either way you want to do that, go through with that process and solve it. You're going to come out with a b value of -16 and an a value of -10. So if you solve those correctly, those are the results that you get. We now know the original function. So I can now look at f of x. If I replace my a with -10, we have that. If I replace b with -16, I have that. So I now know the original function. In this case, what they're ultimately asking for, though, is what's the gradient or what's the derivative when x equals 4. So if I took the derivative function that I had right here, I know that, sorry, let me scoot that over. I know that they're looking for the result when x is 4. So I'm going to take this scenario. I'm going to take the derivative. I can now replace a with -10. I can now replace x with 4. I can replace my b value with -16. And again, I'm replacing x with 4. And so now I know I'm looking for the gradient when x is 4. So if I do all the cleanup on that and simplify all that, then that means the derivative when x was 4 came out to be -352 if you do all the cleanup on that. So this one just came with the extra steps of solving for a and b, and we've seen those throughout several functions throughout the year. That's kind of a popular IB thing to do, is solving for a and b with a system of equations or some method of subbing in values for x and y in order to come up with those. So that's a pretty common thing that we'll be asked to do. But that's it for lesson 3.